Hello, my name is Yaroslava, and I'm presenting our work called Certifiably Optimal Anisotropic Rotation Averaging. Rotation averaging is an important subproblem of global structure from motion pipelines, where we are given a set of images and we build a camera graph, where the nodes encode cameras and edges encode pairwise relations. Each pair of images is used to estimate the relative poses. We are in particular interested in the relative rotations, as illustrated in this graph. Now, our goal is given these relative rotations on the edges to obtain the absolute orientations of the cameras on the nodes. In general, this is done by formulating an optimization problem where the distances between rotations are minimized. If we take a chordal distance, which is a typical choice in isotropic rotation averaging, we end up optimizing the residual rotation angles. Then the problem can also be written in a matrix form like this, where we recall that R tilde is the measurement matrix and R is the matrix of unknown rotations. So we are dealing with constraint optimization problem, specifically with SO3 constraints. This problem is non-convex and has many spurious local minima, but it was shown that the convex relaxation can be obtained with certain conditions for strong duality. We note that to achieve that, one has to drop the determinant constraints. In other words, to optimize over O3 instead of SO3. Now, we would like to propagate the uncertainties in the relative estimates into rotation averaging. Why is that important? Consider this typical two-view example with lateral motion. Here we show how the reprojection errors change from rotating around different axes. If an optimal relative rotation is slightly rotated around z-axis, this will result in higher reprojection error as compared to rotating around y-axis. This means a higher certainty for the angle around z-axis and lower certainty for the angle around y-axis. To conclude, uncertainties naturally appear in the two-view optimization problems. We would like to propagate this information to favor the deviations in the directions of high uncertainty. In this synthetic three-view problem, we have two relative rotations that are accurate and certain, and one that is noisy and uncertain in one of the orientation axes. Our approach relies on certain measurements, and it is therefore unaffected by the noisy, uncertain part of the estimates. Recall that the first step was to solve the two-view pairwise problems. To propagate uncertainty, in each two-view problem, the objective around the local minimum is approximated by this quadratic function. Here, H is the Hessian matrix. The question is, could we rewrite this cost in a matrix form that is admittable by our framework? We show that it's possible. We obtain the new matrix M encoding uncertainty. However, this matrix is almost always indefinite. This is an important note for our next result. If we now replace the isotropic objective by its anisotropic version, we could try to apply the standard relaxation that drops the determinant constraint. Unfortunately, this doesn't work. As we mentioned earlier, the uncertainty matrices are almost always indefinite. This causes strictly smaller objective values on O3 than on SO3, and therefore yields incorrect solutions. In this plot, we show that the rank of the SDP solution matrix X is higher than 3 for standard relaxation, while the proposed relaxation always gives rank 3. In our approach, we keep all SO3 constraints and obtain a new SDP. The key difference here is the introduction of the convex hull constraints. We often get more accurate reconstructions with lower angular errors. These are examples of rotation averaging results on challenging data. And here are some more examples where we compare our approach to the standard isotropic approach, as well as anisotropic cost optimization using standard relaxation. Final note, in this work we used a generic SDP solver which has limited scalability. In the follow-up paper, we introduced a dedicated solver ACD, which is significantly faster. Thank you.